This is a talk I presented at the Free and Open Source Geospatial Conference in North America in Baltimore of October 2023. Let's dive in. First, I'm going to talk about who and what MapLibre is, and specifically what MapLibre Native is, what was the problem with it, how we solved it, and some ideas on what might happen next. So MapLibre is the open source project that took over the old Mapbox GL APIs after Mapbox took them closed source. They forked off the last open version of those APIs and basically started maintaining and now upgrading them. In my experience, the community tends to be a bit more European than American and other areas, although it's growing all over the world. But it does have pretty strong participation from American corporations, and they are providing a fair bit of sponsorship, as are European companies as well. If you're familiar with the open source geospatial world, then you're probably familiar with these two toolkits. They were Mapbox GL and they are now MapLibre. So there's a version for the web that's the most commonly used. It's basically a WebGL rendered map that does vector and image tiles and GeoJSON data and what have you. And it runs in the web browsers. It's JavaScript. And there's a native version, which is a C++ API primarily for mobile, iOS and Android, but also for other platforms. There's kind of a long tail of other lesser used platforms like Qt, Node.js. It's actually used on Windows and Linux too with OpenGL and things like that. So it's not as commonly used, and it's actually, it depends on how you look at it. It's used a lot in end consumer apps, like in Facebook and things like that, but it doesn't have as many developers. And this is typical of mobile and geospatial. But that did present a problem for the open source community. So let's look at what that problem was. To give you the short version, it was technical debt. So in the old days, we used OpenGL ES on both iOS and Android for rendering. So it's an open graphics toolkit, worked fairly well for a long time. But GPUs, that is the graphics processing units that do all our real-time drawing, they changed a lot between when the when the toolkit was developed and now. So Apple introduced Metal, their high performance rendering toolkit, kind of low level rendering toolkit for iOS and macOS in 2014. And then it deprecated OpenGL on its platforms in 2018. And what that meant was that since then, you get thousands upon thousands of warnings every time you compile the toolkit. But more importantly, it meant that if you're making plans for your engineering group or your product development, that you have to take into account that you might lose OpenGL on those platforms at some point. And it's never been clear when that is, although actually it's becoming clear that it looks like they aren't going to allow it or aren't going to support it on Vision OS. So that's Apple's new platform for their headset. So that may be the point at which OpenGL disappears. But if you've been using OpenGL on these platforms, then your support has been declining for years. You don't have the debugging toolkits you'd expect. You don't have a lot of the performance monitoring and things like that. So it's really been lagging. But more importantly, you can't make plans based on that, and that's what really scared users of MapLibre, and that's what had to be fixed. So what are you going to do about that? So OpenGL and Metal are not dissimilar, so you could do a real-time translation layer. There is one, and it does work. You could do something fancy with trying to share the shaders and go to like an intermediate rendering toolkit, something like that. You could rewrite it all from scratch, maybe rewrite it all from scratch in Rust. Why not? Or you could just hope for the best. So that's actually that last one is what most users were doing. They weren't really thinking about it and kind of hoping it was going to be solved for them. Because to be fair, it's a huge amount of work. We like to take this approach. I used to have a startup many years ago where when the salespeople would get a little too creative, we would suggest that they think inside the box. And in this case, thinking inside the box is just implementing Metal. So that's what they decided to do. So the first phase of that was making a plan. So this is an open community, and it was a fairly new one. And the sponsors and the community and the board, they wanted to make sure that everyone's voice was heard, and that the reasons for making these sorts of decisions were open and transparent and so on. So to that end, AWS engaged Stamen, who has a really great reputation in the geospatial community. AWS was involved, of course, being the sponsor, and then the community itself. And then we're sort of the odd ones out here. Wet Dog Weather is my company, and I'll explain how we were involved. But those four groups came together and made a plan. Well, why us? Stamen, Agad, AWS has the money, MapLibre is the community. Who the heck is Wet Dog Weather? We're a software as a service company, and we specialize in real-time weather rendering. So weather apps and dashboards and things like that. That's what we do. We have our own competing toolkit called Whirly Globe, and this actually comes from a consulting company that I owned for quite a few years. So that's our open source toolkit, and we own it. And we made the transition from OpenGL to Metal years ago. Now, Whirly Globe was a competitor to MapBox.gl, and if you haven't heard of it, it was not a very successful competitor to MapBox.gl. It turns out if you're spending a few $100,000 developing a toolkit, it's hard to compete against somebody with 100 million. And that's fine, whatever. We had our own little markets in aviation and weather, and then we eventually just focused on weather, and that's what Wet Dog Weather is. But more importantly, we made that metal transition years ago. I actually thought we were kind of late on the bandwagon there. MapLibre has really pushed it to the limit. And best of all, we were completely unfamiliar with the Mapbox.gl internals. Didn't know how it worked. Even though we knew how to render vector tiles because we do it ourselves, we didn't know how Mapbox.gl rendered vector tiles. So any solutions we brought to the table were going to be different from what they did. And that has some nice implications for intellectual property. So here's what we did. After that first phase where we did a bunch of planning, we came up with this plan essentially, a two-phase plan to actually get the toolkit over to Metal, and while we have the engine open, so to speak, fix a bunch of other stuff. So the main goals were of the first phase, rendering modularization, were to simplify the task of adding a new rendering SDK. So basically, isolate the real-time rendering stuff. Not as like an overlay. A lot of people want to do it as like an abstraction so that you could target multiple toolkits with the same abstraction layer. It's really not what we were trying to do. We were trying to just kind of isolate the OpenGL specific stuff so that we could drop in versions related to Metal. It's a little bit of a different approach, and it doesn't assume that you have to abstract away absolutely everything. So yeah, the specifics get pretty interesting. And then also modernize the renderer as well. So you wouldn't design this renderer the same way now that you would have 10 years ago. And since we were going to be working with a multi-component team, people from different companies, and some people had just been hired, we wanted a way to warm things up a little bit. So have the team work together before you get into the nitty-gritty of Metal, and start on some of the secondary goals. We had a bunch of secondary goals beyond just doing Metal. Phase 2 was get direct Metal rendering working, and then a whole bunch of secondary goals. So we'd like to move things to the GPU. So what that means is that in a modern rendering toolkit, you would actually do a lot of the frame-to-frame work on the GPU. So if you imagine a standard vector map that you might look on it on your phone or on the web, as you zoom in, a lot of things are changing. Frame to frame, like roads may be getting wider as you zoom in. Symbols might get bigger. Colors are going to change as one layer fades into another, opacity, all sorts of stuff. There's actually a lot of moving parts there. Most of those parts should be moving on the GPU these days, and we'll talk a lot more about that. So modern mobile devices have a lot of cores, so just like desktop does, so a lot of individual CPUs, as it were, sort of. You really ought to be doing most of your work on separate threads with just the main thread doing the rendering. We wanted to be able to replace shaders. Shaders are the code that the GPU runs. Wanted to be able to add new layers and replace old ones and reuse some of the geometry creation. And I'll talk a lot more about that later. So that was the plan. How did we implement the plan? Well, MapLibre provided the direction, so a lot of interaction with the board and the technical experts. AWS provided the money because money, and we did the engineering management and some of the implementation. So we're actually running the project with myself as the lead. And we've got our people involved. We've got two AWS developers, one developer from Meta, and a developer from Grab participated for a while as well. And then we work with the MapLibre native maintainer fairly closely because obviously they're going to have to take control of this after it's all done. So the general goal to start was multi-SDK support. So we're always going to have to support more than one rendering SDK is the idea. OpenGL ES for Android going into the future, even though there is Vulkan, you're probably still going to have to support OpenGL ES for Linux and Windows through this translation layer and all sorts of other good stuff. You can't really take that away. So you're going to have to support that and Metal and whatever else gets added in the future. Um, yeah, Vulkan, DirectX, WebGPU, whatever else. So it really needs to be abstracted, but also still fast. The primary goal, obviously, was to support Metal. That was the existential problem with MapLibre Native. Is it, by not supporting Metal, um, you're kind of going to end of life the toolkit on iOS pretty quickly, and that's just not really acceptable in the mobile world. Everyone who develops a mobile app needs to be able to know they can get to the other platform just as well. So we were starting with a direct rendering mode. Now, direct and indirect are kind of interesting concepts. Direct rendering is the most like OpenGL. You basically say it's been a long time since you told the GPU draw a triangle. More likely, you tell it draw a million triangles, or you tell it here's a big pile of data, just figure it out. That's kind of where things are going. Um, but it's a continuum. So you can tell it draw 20,000 triangles, and that's about where you want to be. Like you don't want to be doing individual triangles, but you do want to be doing big groups of triangles. And that's direct mode. It's like draw this group of triangles onto this next group of triangles. Okay, now get it all to the screen. So the rendering mode for Metal should be much faster than OpenGL if you're not CPU bound. Indirect mode is a little bit different and very interesting. It's more like what modern GPUs like to do, which is to say, give them a pile of data and have them figure it out. To a certain extent, there's a lot of caveats there. Um, but the idea is essentially that you encode everything ahead of time, and then you just refer to those encoded command buffers later. So it's like you aren't re-encoding everything every frame. You're just kind of referring to what you encoded before. So you might, for example, say these 10,000 triangles. Well, I'm not referring to 10,000 triangles now. I already set that up a while ago, and now I'm just referring to the thing over here that we already encoded. And then the way you control that is by tweaking the various, kind of uniform buffers, you call them. Basically, the parameters that control where that's displayed and what it looks like. It's blazingly fast. It's incredibly fast because it doesn't have to talk to the CPU as much. It can just do its own thing. It's way more structured, and it was a secondary goal because it's hard. So, how did we do with Metal? It's an unqualified success. It's working. The direct mode has been working for a while. It's about as fast as OpenGL, and the reason for that is it's largely CPU bound. What that means is that we're doing way too much work on the CPU to get things set up and encoded, and there's a lot of reasons for that, some of which we'll try to address before the end of our project, which ends in November, and some of which will have to keep being addressed as time goes on. Indirect mode we did not get to. Again, that's because there's too much going on on the CPU at any given time, and it's not going to work very well until that's addressed. All right. We added a secondary goal on the way, which is to upgrade OpenGL ES primarily for Android. So there's three major versions of OpenGL ES that you might hear about. 1.0 was a fixed function pipeline. That means no shaders. 2.0 added shaders. Essentially you could control the code that was run on the GPU. 3.0 really made this mature and added UBOs and VAOs and instancing. You don't have to understand what any of that stuff is. We're using 2 out of the 3 now. They really help with things, and they let us kind of consolidate uh, our MapLibre data structures in a way that works well for modern toolkits. Um, but there's room for improvement there. So once you get to OpenGL ES3, there was a syntax change in the shaders, and there's the way things are structured is a bit different. But once you do that, it's easy to add features for 3.1 and 3.2, including compute shaders, which is great for all sorts of stuff, and all sorts of other goodies that they added in more modern versions. And this is the path for Android. Yeah, Vulkan would be great, and it would be great to add that, but I think a lot of people are going to still be using OpenGL ES on the Android for the foreseeable future, not to mention Linux and Windows. So by upgrading to 3.0, we made that hopefully faster, but definitely better. A secondary goal was making it more user serviceable. So the way MapLibre Native is implemented is very clever, but not very modifiable. It depends heavily on C++ templates, and it's very difficult to fix things. So the problem with that essentially is if you want to add something new, it's kind of difficult. And if you want to track down a bug, it's also kind of difficult. Small changes to how things are rendered will cascade up and down in the template stack. And in particular, the style support for style sheets is very oblique. It's hard to understand. Fast, but difficult to get to do something different. All right, and as to how we did on that goal, uh, it's mixed. The results were mixed there. So we can now drop in new rendering SDKs. So that's pretty good. Touring the code was pretty good, seeing different parts of it, fixing different parts of it, updating the build system. That was largely the maintainer doing a lot of that, but we contributed as well. And the shaders are disentangled, which is helpful. I'll explain more about that in a minute. The tangled thicket of metaprogramming is still there, particularly around the style. So we managed to push it back from the rendering, which certainly helps us implement and debug things, but we were not really able to get it out of the style sheet implementation without rewriting that, and that wasn't something we wanted to do. So mixed, but positive. All right, in terms of upgradability, we wanted to be able to replace existing shaders. So the way things were structured when we got the toolkit, all the shader source code, and again, as a reminder, shaders are the code that runs on the GPU. So what controls how triangles and points and all that great stuff looks. And that's just how modern GPUs work. All the shader source code was stored in this compressed blob of data, which they would just pull random bits out of as they needed. It was incredibly clever. It was very small. It worked great, but you couldn't modify the stuff. You had to rerun this script, and it's just not the way you want to work if you're debugging. Like particularly with Metal, you can actually kind of step through shaders in Metal. Same is probably true for modern stuff on Windows, but this is really great. But of course, you can't really do that if all your shader source code is stored in this weird blob. So that was difficult to modify. Replacing existing layers almost impossible without recompiling the toolkit. We wanted ways of doing that, adding new layers, and hopefully add some more examples for these things. That turned out pretty well. We can now add and replace shaders. So the shaders are stored in individual files, which can be edited using using the kind of the correct editor for it on iOS, and then the build system will take care of the rest. Or at least that's mostly done at this point. Should be done by the end of the project. We can add new custom layers, and that's particularly interesting. So the way custom layers used to work in the toolkit was that you kind of had an OpenGL custom layer, and you were told where the map was, like there was a translation and some information about the context and what you need to draw in it. But then you were on your own. You actually had to write OpenGL compatible code. You had to talk to the library yourself, and you couldn't reuse any of the same stuff. So, of course, MapLibre knows how to turn raw data into wide lines and filled polygons with textures and symbols and text and all that good stuff. But you couldn't do that from the custom layers, which makes very little sense if you think about it. What you would like to do is be able to use all the same utilities that we use for turning geometry and text and so forth into raw data to render, or exactly, I should say, structured data to render, But there's no good way of doing that. So that's something that we've added in this project as a way of at least creating fairly simple lines and symbols and filled polygons and all that good stuff from custom layers, which also, as a consequence, makes them cross-platform. So it's written in C++, which you can access, in various different ways, and then you can write the same custom overlay that works both on Android and iOS. And then we probably won't get to it for this project, but then you can write interfaces on top of that for Swift and Objective-C and Java and Kotlin and so on. So that's actually pretty cool, and we're seeing that as the way we want to go in the future for trying out new things. All right, multi-threading was deferred. So, it's complicated. It turns out if you don't design a toolkit with threads in mind, it's really hard to go back and do it later. Um, it's not the implementation here that's such a big deal. It's that it would change how things look, and that's something that we were not prepared to do for this project. So, we've written it up as a proposal, and hopefully it'll be done in the future. The simplest way to approach that might be just to do it for new things. All right, one goal, which was pretty important, was trying to move more work to the GPU. This is beyond just getting things working. This is trying to make them work better. So there's too much fiddling around on the CPU, and when you're doing that, that means the GPU can't work independently. The way these two parts of the system operate is that the GPU is a very fast engine, but not very flexible one. You want to get it primed and let it do its thing, and then you don't want it to have to wait on you for little bits of information. And if we're encoding everything for every piece of data, every frame, even if we've grouped those pieces together pretty well, that's too much talking to the GPU. What you really want to do is get things set up and then let it do its thing and only modify the data it's dealing with when something changes. Um, so what that means for a vector map is that we want to move a lot of the style logic. So as you zoom in, the color of things will change, the opacity of things will change. Some symbols will get bigger, others will get smaller, they'll fade out, all that good stuff. So that's what we wanted to move to the GPU. And as you can imagine, it's pretty simple logic. Most of the expressions are pretty straightforward. GPUs can handle even fairly complex expressions. It's more just a matter of what data they're depending on. So anything that's zoom level dependent should work pretty well. So yeah, that was the idea. Calculation's not that complex. Don't sync with the CPU. Just get it done. How do we do there? Positive but mixed. Here's how it turned out. Moving expressions to the GPU is actually not that hard. Anything that's based on a single value, like a zoom level, is actually pretty easy to move over to the GPU. You just have to communicate the bits you want to move over and then have it do its thing. But here's the weird part. Getting the CPU to stop doing that, the same work that it was already doing, is actually very hard. And this is because of that tangled web of metaprogramming, the C++ template logic around the styles. It was all set up and primed to work as fast as it could on the CPU, manipulating all sorts of data at once. And that was very clever, but now it's hard to turn off. So it's like a clockwork, a big clock with old style clockwork gears and such. If you then move half of its functions over to a digital clock, it's difficult to turn off half the gears, and that's kind of what's happening with the template metaprogramming stuff on the CPU. So we're doing our best here. We're still we moved some of the functions over the GPU, but we're still trying to figure out how to kind of turn off a lot of that logic on the CPU and making progress there. All right, the rest of this is going to be proposals for the future and then a summary of where we were and what we did. So we're a consulting company, What Dog Weather, at least in the geospatial space, product company in the weather space. So we're looking for more work, and we made a bunch of proposals and kind of reworked a bunch of the existing proposals from the MapLibre community. So we did this tour of what people had asked for that that we could understand and were qualified to do, and then threw in a few of our own and talked to the sponsors and made a few more. So these are the outstanding proposals related to MapLibre, particularly native, that we thought might be of interest. So the community wants to do a globe mode. That's pretty cool. You should also do atmosphere and stars because it looks cool, and sometimes cool things are good. Support for 3D terrain is something they have on the web version. I'm moving it over to native would be good. Although it needs a lot of more gesture support. Interacting with 3D stuff is different than interacting with 2D stuff. Doing 3D tiles would also be interesting, and there's some interest from the Cesium community there. And then general map coordinate system support. This one may seem boring, but it's kind of important to a lot of government users. So currently, MapLibre maps are displayed in Web Mercator, which is this unrolled latitude longitude thing that does a bit of math, and it's not something that cartographers like. So what you really ought to do is to display any map and any coordinate system specified by the developer, and then reproject any of the data, which is in its own coordinate system, on the fly. OpenLayers does this. Whirly Globe does this. A lot of things do this. So it's certainly doable, but it is a lot of work, particularly for a real-time toolkit. But it opens up new markets. It lets you sell your, or at least have your toolkit be adopted by governments um, more widely, I should say. All right, there were a set of proposals for performance and expandability. As I said before, the threading support, we turned that into a proposal because we didn't get to it in this project. And then we also proposed a general purpose data loading architecture based on the one we have in Whirly Globe. What this means essentially is that currently MapLibre Native in particular really only reads GeoJSON and vector tiles, and you can try to shoehorn other stuff in there, but it's a little difficult. The web version has this add protocol support, which makes it a little bit easier to do that, but native doesn't really have that. So we proposed a way to add a lot more data formats to the system. Yeah, so there's that. There's OpenGL optimization. So OpenGL is definitely not dead, certainly not on Android, and it could be a lot faster. The way the toolkit was structured for OpenGL ES2 made it do a lot of things that were kind of non-optimal. There's no instancing to speak of and all sorts of good stuff. So you could make OpenGL ES3 support much faster, particularly for Android. And then there's optimizing loading experience and for slower connections. That's just kind of a grab bag of ways to make the bad network experience much better. So there's some proposals related to rendering SDKs. WebGPU is this new standard for not just for the web, but just kind of like a consolidated GPU standard. Would be interesting to support. Vulkan is kind of the reaction to Metal, or maybe it predates Metal, but it's the equivalent of Metal for Android and Linux and a bunch of other devices. It supports Windows too. Vision OS is Apple's new headset OS. You have to see how that one plays out. Vulkan's probably worth doing. WebGPU, if somebody wants to pursue that. Vision OS, I'd wait. All right, there are proposals related to style. So currently, the native version of the toolkit doesn't support a bunch of stuff in the style spec that the web version does. Obviously, parity would be good. The MapLibre community is debating about whether or not to have a style editor. And we put together this, I thought it was an interesting proposal for an optimized vector map pipeline. And the idea there is that style sheets and vector tiles are way too flexible. And that if you want to write a really small and fast rendering toolkit for vector tiles and the standard style sheets, you need to turn them into something simpler, which is probably doable. So you need to start treating styles as just an input, and lint them and compile them into something that's much more optimized, which could be simpler. And you need to do the same thing with vector tiles, tessellate them, and you could also at the same time encode them differently. There are better ways of doing that now, and just make them more straightforward. So currently with a style, you might specify everything that matches, that has this attribute with this value is a lake and should be colored blue. The better way to do that, at least for simplicity, would be to say, okay, all these polygons are style number 5, and just with a simple lookup. So obviously you don't want to edit that way. So we're just suggesting there should be a pipeline to get to a simpler way of doing things, so people could write simpler vector map toolkits in different languages and try out different things. There's also a static map rendering optimization proposal that's interesting for essentially rendering static maps. So what did we learn in the course of this project? Style sheets are complicated, and the logic related to rendering them is also very complicated. It doesn't need to be as complicated as it is. We've tried to make it a little bit simpler internally, but that's going to be an ongoing problem. Thread support after the fact is hard. It might be simpler to approach that with new projects in the toolkit rather than trying to restructure the old stuff. Then maybe go back if it works well. And there's lots of room for improvement. Switching more things to the GPU would be great. Adding new components to the system could use some work. And of course, there's always documentation. So how did it go? The native metal port was successful. We can add more SDKs in the future, Vulkan if somebody wants it, others, which sort of future proofs the toolkit. So now of course, they've got the web version, they've got the native version, they can support multiple SDKs. That should future proof things for a while. We addressed a bunch of the secondary goals, deferred some, and then kind of made middling progress on others, but they were secondary goals, so that's kind of how that goes. And the sponsors were happy and looking to do more, which is really all you can ask for.